Good morning, grade 11. This is Mrs. Pascale. Today we will continue chapter 4, section 4.8, complex numbers. The objective is to perform operations over complex numbers. We'll start by reviewing the previous operations. Simplify each expression. Example 1, 2 plus 4i plus 4 minus I. To add two complex numbers, we need to add the real part with the real part and the imaginary part with the imaginary part. So we get 6 plus 3i. In example 2, minus 3 minus 5i plus 4 minus 2i. We need to add the real part with the real part and the imaginary part with the imaginary part. So we get 1 minus 7i. In example 3, to add 7 plus 9i plus negative 5i, we only have as a real part 7, so we write 7 and we add 9i with negative 5i and we get finally 7 plus 4i. Subtracting 12 plus 5i from 2 minus I, after reducing the expression, we get 12 plus 5i minus 2 plus I, so it gives 10 plus 6i. In number 5, subtracting minus 6 minus 7i from 1 plus 3i, we get minus 6 minus 7i minus 1 minus 3i, and it gives minus 7 minus 10i. In number 6, multiplying 8 plus I into 2 plus 7i. After expanding this expression, we get 16 plus 56i plus 2i plus 14i squared. Replacing I squared by negative 1 and adding the two imaginary parts, we get 16 plus 58i minus 14. So 2 plus 58i. Now in example 4 we have 9 plus 4i to the power of 2. It's in the form of the perfect square a plus b squared, so it should be reduced in the form of a squared plus 2ab plus b squared. So expanding this expression, we get 9 squared plus 2 into 9 into 4i plus 4i squared. And after reducing this, we get 81 plus 72i plus 16i squared. Remember that I squared is equal to negative 1, so the final answer will be 81 plus 72i minus 16, giving 65 plus 72i. In example 8, the calculation or to simplify 1 minus I squared, we need to apply the remarkable identity rule of perfect squares. So we get 1 squared minus 2 into 1 into I plus I squared. Replacing I squared by negative 1, we get negative 2I. In example 9, 1 plus I into 1 minus I, it's in the form of a plus b into a minus b. It gives the difference of two squares, a square minus b square. So 1 square minus I square. Replacing I square by negative 1, we get 1 plus 1 equals to 2. In example 10, 9 plus 4i into 9 minus 4i. Expanding this expression, we get 9 squared minus 4i squared, so it gives 81 minus 16i squared, so 81 plus 16. When we replace I squared by negative 1, and we get 97. In example 11, calculating minus 6i squared gives 36i squared. Replacing I squared by negative 1, we get minus 36. Example 12, 2i cubed. It's 2 to the power 3, I to the power of 3. 2 to the power of 3 gives 8. I cubed should be written in the form of I squared times I. By replacing I squared with negative 1, we get minus 8i. 2i to the power of 4 equals 16i4, so it gives 16i squared to the power of 2 equals 16 into negative 1 squared, so equal 16. The last operation we will talk about is dividing complex numbers. How can we find the quotient of two complex numbers? In example 1, 2 plus 3i over 1 minus 4i. Finding the quotient of a complex number mainly depends on reducing this quotient or writing this quotient in the form of a plus ib. So basically we need to remove or change the denominator from the complex form to a real number. How can we do that? We need to multiply and divide this fraction by the conjugate of the denominator. So as you see in example 1, the denominator is in the form 1 minus 4i. Its conjugate is 1 plus 4i. So we multiply and divide this quotient by 1 plus 4i. And after reducing the obtained expressions, we will get a number in the form of a plus ib. So in example 1, after multiplying by 1 plus 4i, we get, and dividing, by 1 plus 4i, we get 2 plus 8i plus 3i plus 12i squared over 1 square minus 4i squared. It gives 2 plus 11i minus 12 over 17. Writing this quotient in a complex number form, it's minus 10 over 17 plus I 11 over 17, where minus 10 over 17 represents the real part of this number and 11 over 17 represents the imaginary part. In example 2, reducing or dividing 5 minus 2i with 3 plus 4i, we need to multiply this fraction by the conjugate of 3 plus 4i, which is 3 minus 4i. So we multiply and divide by this term. And then after reducing the expression, we get 15 minus 20i minus 6i plus 8i squared over 3 squared minus 4i squared. It gives 7 minus 26i over 25. Writing this quotient as a complex number, we get 7 over 25 minus 26 over 25i, where 7 over 25 represents the real part and negative 26 over 25 represents the imaginary part. We know that a complex number is defined by z equal a plus ib. But for any complex number with a equal to 0, it's called a pure imaginary number, like shown in the previous example 8. Or when z is equal to 2i or z equal negative 5i. For any complex number with b equal to 0, it's called as a pure real number, like example 9, 10, or 11, previously shown, or z equal 5 or z equal negative 10. So when we work with complex numbers, we may get either a pure imaginary number when no real part is shown, or a pure real number where no imaginary part is shown, or as in general, a real part and an imaginary part. Please perform the following operations. Homework is due to Wednesday.